So in last class, we were talking about ideal IV characteristics. So, and we finished here with the ideal IV characteristics, and this is the summary of same ideal behavior for PMOS transistor. Because up until previous slide, whatever we have discussed, those were in terms of NMOS transistor. This is just a summary of the same discussion for PMOS transistor. So now we are going to look at our preference, explanation of our preference, why NMOS transistor is preferred for binary logic 0, why PMOS transistor is preferred for binary logic 1. So that is the fundamental definition of CMOS circuit. CMOS means complementary MOSFET. So CMOS circuit means any logic circuit that is implemented using complementary MOSFET technology. In that complementary MOSFET technology, NMOS transistors are used for implementing whenever you need binary logic 0, that is low output, and PMOS transistors will be used for producing binary output 1 when you need high output. So now in the next few slides, we are going to discuss, based on what we have learned so far, about their operating condition, cutoff linear and saturation region operating condition, why they are preferred for certain type of application. Something is wrong. Slides are not coming in the right order. It is it says by 7. Yeah.
Went from page 7 to page 29, back to page 7.
Yeah. That's not. So this is a practice problem. I want each one. Solution is already there, kind of hints. So I want each one of you to solve this problem. And this will be the exact type of problem you will be given again in the homework, practice homework, as well as in the exam. I want you to basically, it's an implementation of the ideal current equation we just learned. So please solve this problem at home. So pretty soon I'm going to upload the homework along with the solutions. Your job is to solve the problem by yourself first and double check with the solution and submit it as it is, because you will not be penalized for not doing it correctly, because this homework is just for you to practice, and anybody who completes the practice, so will get full marks, 5 out of 5. So today we are going to discuss, as I said, comparison between NMOS and PMOS transistor. So we'll start with the statement, NMOS is a good pull-down device. So in CMOS circuit, transistors have two tasks. Either they pull down the output from high to low, produce a binary 0, or pull it up from ground to VDD or high to produce a binary 1. So whenever you need an output low or binary 0, you have to pull down the output voltage from high level to low level. So you will get a perfect binary logic 0 if you can bring down the output voltage all the way to ground level. If it is slightly distorted above ground, that means you have a distorted, noise affected binary 0 signal. When you are pulling it up, when you are requiring a binary 1 output, if you can pull the output all the way up to supply, supply is the maximum you can go, ground is maximum you can go down, right? If you can pull up the output voltage all the way to the perfect supply level, then you have a strong binary 1 signal. But if it stops slightly below VDD or supply level, you still have a high logic output. Still it will be considered as a binary 1 output, but it will be slightly distorted. So throughout the next 4 slides, we are going to see that NMOS is very good at pulling down, that is producing perfect binary 0 right at the ground level. But it is not very good at producing binary 1. It will always produce a high, but it will be slightly distorted below supply. PMOS is opposite. PMOS, we will see that it is very good pulling up device. It can pull up all the way to supply to produce a perfect binary 1. But when pulling down, PMOS cannot pulling down all the way to ground. So it will always produce a distorted binary 0. So before we move to this slide, we have to first clarify some add some additional clarification between the naming of the source and the drain. If you look at the transistor structure, it's a PMOS transistor, it doesn't matter. Heavily doped source and N-type region, they are identical region, identical in terms of material property, in terms of structure. In all the slides, we are always showing the left one is the source, the right one is the drain, but that is not the case. The naming, drain and source are interchangeable. It depends on, naming depends on how you connect the voltages. In case of PMOS, we know that source and body, we always know that source and body should be tied together. In case of PMOS, they should be tied together and connected to supply. So whichever terminal in PMOS is connected to the supply, that corresponding region takes the name or function or the role of the source. And the lower terminal potential will be the drain. Gate is unique. You cannot replace gate. But the source and the, now you connect supply here, this becomes your source terminal. If you connect supply here, this becomes your source terminal. So things to remember, in case of PMOS, the between source and the drain, the higher potential terminal acts like the source. In case of NMOS, lower potential terminal acts like the source because it has to be connected to ground. So if you know that, then it will be easy. And if you change the polarity, they change the name and role. So we want to see why NMOS is a very good pull down device. That is why it is able to produce perfect binary level. To test it, let's say we have a random output capacitance in certain logic circuit, and it is holding across the load capacitance a high perfect VDD, a high value, a logic 1. And by some logic operation, using this NMOS, we want to pull down this high to low, that is we want to now convert this from binary 1 to binary 0. While doing it, I want to see, can this NMOS transistor bring down this output node voltage all the way down to ground? If it can take it all the way down to ground, 0, that means it is very good pulling down device. It can produce perfect binary 0. So now, let's say this side we want to pulling it down. So let's say this side we have to connect it to ground to drain the voltage here, right? So first connect the transistor between the output node and the ground because we want to discharge it, pulling it down. The next thing, we have to turn the transistor on by applying a supply voltage at the gate. We want to turn it on strongly, so we will apply maximum possible voltage at the gate. It is turned on. So now, and this side is connected to ground. The moment this side is connected to ground, it takes the name and the role of the source. And the drain is higher, it is the drain for NMOS. So now, what I have, this side is connected to supply VGS for this NMOS transistor is equal to what? VDD, because this connected to VDD, this connected to 0. So if VGS is equal to VDD, this transistor will remain on because it is much larger than threshold voltage, so it is in on state. If the transistor is on, this load node is now connected to the ground because the transistor is on. What will happen? Discharge will take place. So this transistor will remain on for how long? As long as VGS is over threshold voltage. No matter whether it's linear or saturation, it doesn't matter when it is conducting. But the first condition is VGS must be greater than threshold voltage for the transistor to remain on, for the output node to get discharged. But we connected this node, gate node to the supply, this node to the ground. So no matter what happens here, this voltage VGS for the entire duration of operation will remain equal to VDD, because gate is VDD, source is connected to ground. So if it remains equal to VDD, much larger than the threshold voltage, it will remain on for continuous duration of the operation. So this output voltage can discharge all the way down to ground. How long a current will continue? As long as there is a voltage difference. So this voltage must and will come down to 0 for the current to stop. That means by the time the transistor is turned off, it has taken down this output voltage all the way down to 0, because the transistor remains on for the whole duration. It never stops because VGS is always greater than VDD. So that's why NMOS transistor is very good at pulling down. So it's a very good pull down device. That's why we use it in the block of logic circuit where you need to produce a binary 0. Now let us look at the opposite scenario. Same circuit, different scenario. Let us assume that now for the same circuit, initially the output node is holding a binary logic 0. That means across the load capacitance, you have 0 voltage accumulated. Now, using this NMOS transistor, I want to pull that output voltage to high, want to produce a binary 1. So the moment you connect this terminal to anything that is holding a 0 voltage, it takes the name and the role of the source. Now I want to pull it up. To pull it up, I have to inject voltage into the load capacitance, output capacitance. So I have to connect supply here to inject voltage current into this direction. So the moment I connect supply here, it takes the name drain. Now I have to turn on the transistor. So the gate is connected to supply. So the gate is higher potential, source is initially 0. So the transistor remains on because source is initially 0. This side is connected to supply, the drain is constantly at high voltage because it's supply. So the moment the transistor is on, it will inject charge. As it injects charge, this load capacitance will get voltage accumulation. So across the load capacitance, the output node voltage will go up and up because you are filling the capacitance. So how long that filling will continue across that CL? Initially, VCL or V output was 0. As you are injecting charge from drain, transistor is like short, it's on. As you are injecting it, this voltage is going up. Initially 0, maximum it can go up to theoretically maximum VCL can go up to VDD. But the question is, as we are going up and up, at one point, if this maximum voltage reaches VGS minus VT, that is VDD minus VT, because we applied VDD, right? When VCL becomes equal to VDD minus VT. So, at the drain, I applied VDD. As you are increasing the voltage across the load capacitance, at one point, this will become, because it is increasing from 0 equal to VDD at the source end. So, what is VDS? VDS is the voltage difference between drain and the source. If this side is connected to 0, VDS is actually voltage applied at the drain. But in this case, that is not the scenario. In the source voltage, initially it was 0. As we are injecting, voltage across this capacitance is going up and up, up. At one point, it will reach a point slightly below VDD, which is equal to VDD minus VT. At that point, this drain voltage is VDD, this gate source voltage is VDD minus VT, right? That becomes equal to VT. So, if this is the case, then what happens? Sorry, VGS. VGS is VG minus VGS. I'm trying to whether the transistor is on or not. So, gate source voltage between gate and source terminal. Gate voltage is constant at VDD, but the source voltage is going up. So now, at gate voltage, we applied VDD. At the source, this voltage was initially 0, and at one point, it will go up to VDD minus VT. So, at this point, when VCL equal to this, gate voltage becomes, effective gate source voltage becomes equal to threshold voltage. At that point, transistor enters into cutoff region. The transistor is off. So no further injection of voltage into the load capacitance can take place, because the moment effective gate source voltage becomes equal to threshold voltage or less, the transistor is off. Even if drain has a supply connected to it, it cannot inject anything. So what is the maximum value of load capacitance voltage can go up to? Always the maximum possible pulling up that NMOS can do is always one threshold voltage less than VDD. So it is still very high because threshold voltage is very small, a fraction of supply, but it is ideally to get a strong binary 1, we want an output signal exactly equal to VDD, because that is the highest, strongest possible voltage value. But now NMOS stops at here, so NMOS still can produce a high output, but it will be distorted by the amount of the threshold voltage. So if your output is distorted at the beginning, during the circuit operation, what will happen? Any noise or anything can push that signal out of the boundary and you may get an erroneous output, right? Because to have a signal right at the ground for binary 0, right at the supply for binary 1, you have very strong signal. So the noise, you need much larger amount of noise to distract it from high and low level. But if at the beginning, if you produce binary 1 using an NMOS, the signal itself inherently is distorted or reduced by the amount of the threshold voltage of this NMOS transistor. That's why NMOS is a bad pull-up device. It's not a very good, efficient pull-up device. So that's why we don't use NMOS for producing binary 1. Now let's do the same analysis for PMOS transistor. PMOS is a very good pull-up device. How? Let us assume that at the beginning, across this capacitance, I have 0 voltage accumulated, so the output is reading 0. Now I want to convert that output, because it's a binary logic, I have to convert it from 0 to 1 or 1 to 0. That's the two operation we do in any logic circuit. So I want to convert it to 1. Now I want to see whether this node can go, using this PMOS, I can take this node all the way up to VDD or we get it distorted. So now to charge it, to charge this output node, which is 0 initially, I have to connect supply here. The moment I connect supply here, this becomes source for the PMOS, right? In PMOS, highest potential terminal is source. And this, it is connected to 0, it takes the name and role of drain. Now I have to turn on the transistor. To turn on PMOS, it's a negative logic, so I have to apply ground potential here. It's connected to ground. So initially, VSG is equal to VDD minus 0, VDD. And even at the end of the operation, still VSG will be equal to VDD. Why? This side is connected to supply, this side is connected to ground. No charging, discharging taking place here because it is supply, it is ground. Charging and discharging is taking place here. Initially it is 0. The moment the transistor is on, I am injecting voltage into the load capacitance. The load capacitance voltage like this will go up from 0 voltage to all the way upward. What is the maximum value this VCL can go up to? VDD, because this transistor will never stop. Like in the previous, it will stop slightly below threshold voltage. Here, this PMOS will never stop because VSG will always remain equal to greater than magnitude of the threshold voltage. Here we say magnitude because it's a PMOS. So it will remain on unless this voltage and this voltage becomes equal. Effective voltage difference 0, only then current will stop. So for the current to stop, this one must go all the way up to VDD. So that's why PMOS is very good pull up device. That's why we use PMOS for binary logic 1 or pulling up. Now PMOS is not a very good pull down device. Same logic. We start with initial high across VDD, across load capacitance. We are to pulling it down. The moment we are saying that this is initially high, this becomes our source terminal. To discharge it, this side we have to connect it to ground. Right? So it becomes our drain for PMOS. To turn on the transistor, we have to connect ground here. So initially, source voltage is equal to VDD, drain voltage is equal to 0. So VSG is initially equal to VDD. The transistor is on, this side is connected to ground, discharge will take place, voltage will go down from VDD downwards towards 0. Now I want to see whether it can go all the way down to 0 or not. So initially, we started VCL equal to VDD. As discharging is taking place, it is going down. My final destination is 0 to produce. However, initially VSG is equal to VDD minus. So VDD minus VCL, right? Sorry. Yes. So source is connected to VDD. Initially, source is connected to VDD and ground is connected to 0. Right? Gate is connected to 0. But the problem is, this is initially the VCL equal to VDD. But as I am discharging the capacitance, load capacitance voltage is no longer remaining at VDD because I am discharging it. So it is continuously going down as well as this effective value of VSG because the source voltage is going down because source is the output node. So a better way to write it is, in this case, VSG is equal to VCL minus 0 because 0 at the gate, at the output initially VCL. So VCL was initially VDD and is going down and down. How long this transistor will remain on? Until it becomes equal to the magnitude of the threshold voltage. So it is going down from VDD. At one point, when the VCL, the load capacitance voltage, becomes equal to the threshold voltage of the PMOS transistor, that this difference becomes equal to the threshold voltage. At that point and below, the transistor is off. So further discharging cannot take place. So the output node voltage cannot go all the way down to ground. It will stop at one threshold voltage above ground. So I will have a distorted output low. That's why PMOS is not a very good pull down device, and that's why we do not use. But earlier generation of Intel microprocessor, they didn't have the industrial processing capacity to integrate both NMOS and PMOS together. That's why they used NMOS only or PMOS only, with the knowledge that one logic operation will be slightly vulnerable to noise compared to the other. So these 4 slides tells you the reason behind choosing NMOS for binary 0, choosing PMOS for binary 1. Logically, you can implement pull-up block and pull-down block using NMOS and PMOS any way you want. But from performance and reliability point of view, it is better and recommended to use PMOS only for pulling up and MOS only for pulling down. That's how the name came CMOS. Any question on these 4 slides? Now, up until now, we are talking about the final output. Okay, if we apply high voltage at the gate of the NMOS transistor, it is on, and then if we apply this much voltage at the drain, it is in linear. This much voltage at the drain, it is in saturation. So up until now, we are discussing what will be the end result for a certain signal applied at gate source and the drain terminal. So that is our static behavior. So for a certain input gate voltage, for a certain input drain voltage, this will be our state of operation. It is on or off. If it is on, it is linearly on or in saturation on, right? So we are only looking at the end result of applying certain signals in the gate source and the drain region. But as we reach to that state from cutoff to linear, linear to saturation, or the reverse, during this transition, that behavior is called transitional behavior or dynamic behavior, right? Let's say if the goal is from here to reach stadium, depending on what path or road, there are like at least 10 different permutation and combination of roads from here to Royals Stadium or Chelsea Stadium, right? Depending on what type of car or a bike you are taking or walking and what road you are selecting, different person will reach to the destination at different time, at different speed, with different level of efforts invested, right? So the cost of final destination, the result will be different. So this selection of methods and ways from initial destination to the final destination, that behavior, that selection is called dynamic behavior or the transition behavior. If you reach to a desired state, the way you reach there, that is called dynamic behavior or transition behavior. And that dynamic behavior of any logic circuit or any system, the behavior during the transition will determine 2 of the most important characteristics of IC, energy efficiency and the speed. So your energy efficiency and the speed will largely depend on the dynamic behavior or the transitional behavior of your devices and circuit. So today we are going to look at what are the parasitics inside the device structure that will determine the dynamic or transitional behavior. So this is what we have been discussing earlier, right? So the structural and the parasitics that will determine the dynamic behavior of MOSFET transistor is nothing but the internal device capacitance. So any electrical device will have three parasitics: resistance, capacitance, and inductance. It's the three basic defining characteristics for any electrical device: resistance, capacitance, inductance. Now, the resistance, when we talk about resistance, the path that is relevant to our current conduction is nothing but the channel. Typically, the channel is too short, too small. It has a very small resistance compared to other parasitics. So typically, for such short distance, at the initial level of analysis, we don't worry about the value of effective resistance of the channel. And for such a short channel, magnetic interference, that is inductance, also will be very, very weak to be considered. So inductance also is ignored for such a short nanoscale dimension of signal power, right? So if we can ignore inductance and resistance for such a short channel, the main factors that will determine the dynamic behavior or transitional behavior of MOSFET is the structural and material capacitances of the MOSFET device. Some of those capacitive components will be contributed by the structural arrangement of the MOSFET itself. Some of those capacitance will arise or vary due to the variation of charge density in the channel. Remember, in the cutoff, there is no channel. Initial stage of linear, there is a strong uniform channel from end to end. As we enter into pinch-off and saturation, the channel becomes weaker and tapered, and at one point pinched off. So the channel charge density varies from cutoff to the end of the saturation region. So the effective capacitance between gate and the channel region depends on the strength of the two conducting plates, gate and the channel. If the channel is becoming weaker and weaker as we move further into the saturation region, so that capacitance between gate and the channel region will take different magnitude or value, or will change in nature depending on the channel charge. So that is the second source of internal device capacitance. And the third source of device capacitance is, here is a PN junction between source and the body. Here is another PN junction between drain and the body. Across PN junction, there is a barrier. For every diode, whenever the barrier is present, across the PN junction, there is a capacitance called diffusion capacitance or barrier capacitance that is present universally whenever there is a PN junction. It is reverse bias condition. Because on one side there is a N layer, another side there is a P layer, positive layer, separated by a depletion layer or barrier. So across them, a capacitance will be always formed. It is called depletion capacitance, diffusion capacitance, or junction capacitance, or PN junction capacitance between this PN junction and this PN junction. So these are the three sources of capacitance that we will see inside the MOSFET device. And then we have to assign any capacitance in a two-terminal device. It has to be measured across two external terminals, right? So in a MOSFET device, how many terminals we have total? 4. Source, drain, gate, 3 active terminals, and the body, the reference terminal. So the PN junction capacitances will arise between source and the body. This PN junction will arise between gate and the body. And then between gate and the channel or gate and the body, there will be capacitances. So since there are 4 terminals, and if we pair them 2 and 2 together, so there will be all together 5 parasitic device capacitance that will appear from these 3 sources. One between gate and the source, one between gate and the drain, one between gate and the body, one between source and the body, one between drain and the body. So inside device, MOSFET device, 5 capacitances, parasitic capacitances will appear between each pair of terminals. There are 4 terminals, so we'll have 5 combinations of pairs, right? So 5 capacitance, and these 5 device capacitances will come from these 3 sources: structural arrangement itself, variation of the or presence of the channel charge, and the presence of the reverse bias PN junction between source body and the drain and the body. So now, so we know the total number of device parasitic capacitance and the source of those capacitance. So we will analyze one source at a time, these 3 sources. But let us now talk more about why dynamic behavior or transient behavior depends on the device capacitance. So, now think about logic output. Logic output is what? The effective voltage at the drain terminal. Drain is your output terminal, right? Drain is, or the source, depending on NMOS, PMOS, which way you are connecting it, right? So your 2 output terminals where signal strength will be measured. Is it a strong one or weak one? Is it strong 0 or weak 0, right? So your output terminal that is as a result of the current or the voltage that is effective at the drain terminal with respect to source terminal. That is your logic output. So what you are doing? You are trying to fill the effective load capacitance CL that is connected to the drain or source. Fill it up or empty it. If that effective capacitance, is it something, a new capacitance you are adding an external? No. That effective capacitance is the result of the capacitance contributed by the device and contributed by the wire connected to the output node of the device, right? So because this output node is what? It is one of the device terminal and it is connected to a wire, signal is sending somewhere. So this output capacitance is not a separate standalone capacitance you plugged it in. It is the total resultant capacitance coming out of the device plus the wire connected to the output of the device. So capacitance is what? It's a bucket of, not water, bucket of charge. If the bucket is larger, you need much longer time to fill it, much more voltage to fill it. So your supply has to be up, your time to fill it has to be longer because your capacitance is larger. So discharge it or to charge it, pull it up or pull it down. You need more charge, more voltage and more time. That means you are taking more time to produce binary 0 and 1. Circuit is becoming slower. You need a higher voltage to fill it up. What you are doing? Your energy efficiency is going down because you are consuming more power or more energy to fill the bucket, the effective voltage at the output node, right? So that is one thing. So now, so we want to make sure that the total effective device capacitance that is as small as possible. That's why as we are cramming more and more transistor, we need to make those transistors smaller and smaller because now there are many more devices, each contributing parasitic capacitance inside the logic circuit. If we do not reduce the total effective capacitance of each device inside your IC, overall capacitance will go up like exponentially. So it will become extremely energy inefficient. To make sure that we keep the energy efficiency and speed under control or delay under control, we have to minimize the size of the transistor to make sure that these capacitances are smaller so that I can charge it and discharge it faster with less amount of voltage. So you see the relation. So that's the transition. If I can reach 1 and 0 faster, then I have faster speed and energy efficiency, and I will be able to do it by playing with the value of this capacitance. So that is one thing. The other important thing to remember, out of these 5 capacitances, only those capacitances that connected to the drain end. Now let us look at 1, 2, 3, 4, 5. Gate channel, gate body. Among these 5 capacitances, this is a required capacitance. Because without the presence of this capacitance, we cannot form a channel. Stronger the gate channel capacitance, stronger the channel, more charge will accumulate, your resistance and channel conductivity, resistance will go down, channel conductivity will go up. So we want, it's a kind of a trade-off, we want that capacitance to be as high as possible to turn on the transistor very strongly to increase its conductivity, to get a stronger channel. But by increasing the gate channel capacitance, we are increasing the total effective capacitance CL, because this also contributing to CL. But this capacitance, one good thing is it is not directly connected to the source and the drain. So it has an indirect effect. But what are the capacitance that are connected directly to the source and the drain? Source body capacitance, drain body capacitance, gate body, source body, this gate source, drain source. These 4 capacitances, they are connected to source and the drain. That is the output node directly. And in my transistor operation, to turn on and off, these 4 capacitance are not contributing anything. The capacitance across the gate body or the gate channel, that is what I need to form the channel. Remaining 4 are parasitic capacitance. It's just draining. When I'm injecting charge from here, here or here, they are just draining my charge, so it's a leakage. So ideally, if you can make them, 4 of them 0, then you have an ideal superconductive device. Ideally, you want this one to be an optimum level, not the lowest, not the highest level. Optimum level to trade off between speed and performance, because you want a stronger, higher capacitance for a stronger channel, but you do not want that higher, stronger capacitance to contribute to higher capacitive load at the output. So we have to come up with the optimum channel, but we cannot avoid this capacitance. So we have to have a certain fixed amount of optimum value of this capacitance to even turn on the transistor to use it. Other than it will be a meaningless device. But these 4 parasitic capacitance, we want to minimize them as much as possible. Ideally, if we can make it 0, because all these 4 capacitance are doing nothing but slowing down the device or taking away some extra charge out of the battery. So these 4 are truly parasitic unwanted capacitance, but anything across gate and channel or the gate and body, that is a required or important capacitance.
So
Yes.
here our focus is to reduce the number of capacitance or decrease
No
the
matter,
size?
yeah, so no matter what you do, so it's a very, very good question. You as the designer, you cannot, it's a physical device, you cannot avoid. These 5 capacitive component will be there no matter what. By changing the dimension, by playing with the material and the doping density, your job to suppress these 4 as much as possible and obtain this value of capacitance at an optimum level dictated by your speed and energy efficiency requirements. So that is the design trade-off you have to do. Try to minimize them as much as possible and try to get the optimum value for this one. Yes.
Since the parasitic capacitances are non-linear, are there different regions of the operation of a transistor where you can minimize the parasitic capacitance more effectively, such as like in the cutoff region versus the
Yeah.
saturation?
Very good question. In the cutoff region, if all effective voltage is 0, so capacitance doesn't affect anything because the transistor is off. But you are absolutely right. Between linear and saturation region, this effective value of capacitance and their impact, physical value of the capacitance will not change, but their impact will change depending on the voltage. Where is the operating point? Because the parasitic charge or noise it will create or take out of the battery Q is equal to CV, effective capacitance time voltage. If you look at the IV characteristics, here, I don't know why it is jumping the slide randomly.
Sounds like a related rates problem. TA calculus.
This should be open.
Yeah, so I have to check. So now, depending on where you are in the operating condition, like here, voltage is constantly changing, or current is changing. So effective C times V will change. So the impact of capacitance, because it's highly nonlinear, that the whole device characteristics will change. So there is another reason in majority, overwhelming majority of the digital application, they always select a fixed point in the saturation region for operating a transistor. Typically, it is at the highest level of supply, VDS equal to VDD, and ground voltage, gate voltage equal to VDD. So that it is strongly in saturation, and this non-linearity effect can be minimized because you don't want your voltage polarity, voltage magnitude at the gate and the drain terminal to change during the operation. Then all these parasitics, their effective value and impact will change. So you are right, the device characteristics, that's actually how they generate the SPICE simulation model. Depending, it's a function of voltage. So as I said, in the regular classroom experiment SPICE we use, that's kind of level 4 or level 5 model. But in actual circuit simulation in commercial tool, we use like level 64 model. All the nonlinearities, all the impacts will be accounted for in those complex analysis. But at this point, for an introductory class, we will kind of ignore that. We will just consider that all these capacitances are constants depending on the device structure, channel charge, and the strength of the PN junction. Now let us look at the capacitive components that are coming out of MOSFET device structures, and then we will see between which component of structural capacitance will go to which two terminals, right? So, first one is gate capacitance. Gate capacitance is the total effective capacitance at the gate terminal, and it is first one is the gate to channel capacitance when there is a channel. So now, before we deep dive into the different components of gate channel capacitance, gate capacitance is the total capacitance effective at the gate. If the technology you have, if it says that your gate capacitance per unit area of the gate layer is equal to COX per unit area, so the total gate capacitance will be basically coming sum from its capacitance with respect to the channel, sum from its capacitance, overlap capacitance with the source and the drain. Now what is overlap capacitance? So earlier we said gate channel capacitance, but now we are no longer saying gate channel capacitance. We are saying that gate capacitance. Gate capacitance will have two components, gate channel capacitance plus gate overlap capacitance. Gate channel capacitance is the capacitance between gate and the channel region. Ideally, the channel length, oxide length, and the gate width should be exactly same, because ideally channel starts from the source end ends at the drain end. Ideally, deposition layer, the silicon dioxide deposition layer of insulation layer should only cover the area between source and the drain. Ideally, gate only should be aligned perfectly above the channel. So, whenever we are talking about gate capacitance, ideally all capacitance of the gate should appear between gate and the channel. But practically what is happening? Practically, once you get a silicon layer, source drain with body, this insulation layer, silicon dioxide, is deposited from the top. It's a liquefied material deposition from the top surface. Can you guarantee that liquefied material will stop at here, right at the edge? No. They will spread and come little bit over the source. They will come and spread over the little bit over the drain. Same thing with the gate material. Highly vaporized, liquefied gate material deposited on the top surface. It will spread left and right. So it will come over source to some degree. So a tiny portion here of gate will overlap with source separated by silicon dioxide. So there will be a tiny capacitance formed between gate and the source. Tiny capacitance formed between gate and the drain, that is called overlap capacitance. Ideally, everything should appear between gate and the channel. So gate capacitance, we have two components due to the real structure of the MOSFET. Real structure will have a portion of insulation on the gate overlapping the source, a portion of the insulation overlapping the drain. So now first look at the gate channel capacitance. So gate channel capacitance is very easy to calculate. If the technology data sheet tells you that per unit area capacitance for this technology is COX, you just multiply it by that per unit area capacitance with the area of overlap between gate and the channel. Area overlap is this dimension times this dimension, right? Because it is overlap. So it is W times L. So we have that gate channel capacitance, and this entire gate channel capacitance will appear between which surfaces? The bottom surface of the gate and the top surface of the channel, right? It will not appear between this one and this one, because the bottom surface of the gate and the top surface of the channel, that's where the gate channel capacitance will appear, and the magnitude will be this, right? Now, the problem is the channel itself is changing, right? Channel itself is changing. Channel is not a constant. In the cutoff region, there is no channel. Channel charge is 0. In the linear region, there is a continuous channel, so the entire capacitance will appear between gate and the channel. In the saturation region, we have tapered pins of channel, so that capacitance will be different from capacitance in the linear. We are talking about the non-linearity, right? So here is the situation. In the cutoff region, there is no channel. So the gate to channel capacitance in the cutoff region is actually gate to body capacitance, because this portion is now part of the body. In the cutoff, there is no channel. So the capacitance, gate to channel capacitance, is actually will appear between gate and the body, and that capacitance will be COX times WL, because then the overlap is L times W, and across this outside per unit area capacitance is COX, that is given from your technology data sheet. So you know that the gate channel capacitance in the cutoff region will appear between gate and body, so we are calling it gate channel capacitance with body, and this is the total amount, right? Yes.
But if there is no channel formed, then why we are considering the length of channel? There.
Well, actually, what is the channel? Channel is this portion of the body.
Distance between.
So when it is inverting the polarity from P type to N type, we are calling it the channel. So when an n-type channel is present here, so this conducting plate and this n-type channel will form the capacitance. No capacitance will appear with the body. But here, so the body will be disconnected from that capacitance. But here, body is the one is directly coming under the contact of the silicon dioxide. So the capacitance will form between gate and the body. But what portion of the body is overlapping with the gate? This length times this width, the area. So that's why this capacitance COX times WL will appear between gate and the body. So it's the channel capacitance, but that will appear between gate and the body. Then now let us look at the linear region. In the linear region, you have a continuous channel from source to drain. So the entire capacitance COX times WL will appear between gate and the channel. But to define a capacitance, we have to assign the capacitance with a pair of terminals. Channel is a floating temporary presence of electron inside the body. It does not have an external connection itself. It is connected to the external world through the source or through the drain. So all the channel capacitance between the gate and the channel must be connected to the source or to the drain to measure it from the outside, to see its impact from outside. So it is a standard practice because channel is uniform from source to the drain in linear region. Half of the total capacitance is assigned between source and the gate. Half of the capacitance is assigned between gate and the drain. So in the linear region, gate body capacitance, channel capacitance will be 0 because the body is separated from this whole capacitive arrangement. There is a layer of N channel sitting there. So gate body is out of consideration. So no capacitance will appear between gate and the body because it's not there. So this component will be 0. But because of the symmetry of the channel and the source of the drain, if I allocate half of the channel capacitance with source, half of the channel capacitance with the drain, so I will get gate source capacitance due to the channel charge will be equal to gate drain capacitance due to the channel charge equal to half of the total capacitance. But in cutoff region, situation is little bit tricky because I have a pinch-off channel. That channel is disconnected from drain. So the two capacitive plate forming the capacitance, one end is connected to gate terminal, the other end is connected to the source terminal. So there is no electrical connection of this channel with this drain. So in the saturation region, the total gate channel capacitance must be placed between source and the gate because this one is electrically disconnected from the channel, right? So gate source, in that case, if we exclude this tiny region, we'll talk about this region, but the capacitance due to channel charge will appear between gate and the source. Now the question is, when you have a uniform continuous channel, the total capacitance value is COX WL. In linear region, in cutoff region, we allocated the entire amount with the gate and body. In linear region, we allocated half and half. But here, the channel itself is tapered. So the total capacitance will never be equal to COX WL because the channel is much weaker and tapered, much shorter. So the total charge inside the channel is significantly lower than what we expect from when a full channel is present. So there is no shortcut way to estimate what is the value of that charge or value of the effective capacitance. It depends on how short and long that pinched off region, right? If the pin stop is much longer, your channel is much shorter and shorter, it will be. But it is standard practice for introductory analysis to assume that on average in the saturation or pinch off region, the total effective capacitance between gate and the channel charge will be 2/3 of what we ideally would estimate for a full channel present. This is just an estimate to make it simple. So, in the saturation region, all the channel capacitance will appear between gate and the source, and it is approximated to be equal to 2/3 of the total capacitance in ideal scenario when an entire channel is present. So, now the question is, in the saturation region, a portion of the body now appears directly under the gate. So in the saturation region, actually there should be a gate body capacitance due to the presence of this pinch off region. But again, at the introductory level, we are assuming that that capacitance is very small compared to other components, so we will ignore that. But practically, when you do high performance analysis, that cannot be ignored, because a portion of the gate directly coming in capacitive arrangement with this small portion of the body, because that body is appearing directly under the gate. So a capacitance will appear whenever two electrical conducting plate or surface appear across an insulation or barrier. Then capacitance will be formed. So in this case, it is not happening. So the gate, so now let us summarize. The gate capacitance, all the capacitance that is appearing across the gate due to the channel charge. It has three components: gate to body, gate to source, and gate to drain. And the contribution in each three capacitance will vary depending on whether it is cut-off linear or saturation region. So that is for the capacitance due to the channel charge. But gate capacitance has another component, overlap capacitance, because of the overlap of the gate and insulation over source and the drain. So ideally, if we draw a cross section this way or this way, we should see that source, insulation, and channel and the gate, everything is aligned in this line. In this line, there should not be any overlap. But let's look at a practical scenario. Practically, what will happen? Actually, insulation and the gate will come little bit over source, little bit over drain. This is a side view. Now, if I take a top view from the top, what do we see? This is the insulation and the gate layer, this green portion, light green portion. As you see, it is coming over by amount XD over the source, by amount XD over the drain. Since materials are deposited uniformly from the top, we can assume that it will spread equal amount on the drain end and source end. So this length or the width of this overlap XD will be equal on the both sides, right? So this is the top view of the transistor dimension, gate overlapping with the drain and the source. This is the side view, right? So now there will be two overlap capacitance, one between gate and the source, one between gate and the drain. So overlap capacitance, since we are assuming that the spread of the overlap will be identical on the both sides, so gate source overlap capacitance will be equal to gate drain overlap capacitance. Will be equal to what? In that channel area, from technology, we know that per unit area capacitance is COX. It's a technology constant. Now, what is the area of this overlap? This is the width of the transistor, and XD is the length of the overlap. So the area is XD times W. So this overlap capacitance with source and overlap capacitance with drain with respect to gate will be COX XD times W. Right? This is the general definition of capacitance. So now, if we want to summarize all the capacitances that is coming associated with the gate terminal, gate body capacitance in the cutoff region, the entire portion of channel capacitance will appear between gate and the body because there is no channel. So entire capacitance across the gate junction, across the gate insulator in the cutoff region will appear between gate and the body. In the linear region, body is disconnected, zero capacitance. In the saturation region, by ignoring the tiny area of the body, we can say that gate body capacitance will be zero in saturation region. But in linear region, gate source capacitance. So now let's talk about gate source capacitance. Gate source capacitance in the cutoff region, there is no channel. So no capacitance exists, so there is nothing to distribute. It is zero. In the linear region, half of total capacitance will appear between gate and source. Half of it will appear between gate and drain. But in saturation region, nothing will appear between gate and drain because it is disconnected from the channel. We assume that everything will appear between, we know that because it is connected with source, everything will appear between source and the gate. In cutoff region, the channel capacitance, but its magnitude will be 2/3 of the maximum possible value because the channel is tapered. Gate drain, zero in the cutoff, half in the linear, zero in the saturation. So if we now add them together, the total effective capacitance in the cutoff region in the gate due to channel charge is this. Total effective capacitance in linear region is this. Total effective capacitance in saturation is much less, 2/3. Now, and this is the summary of gate to channel capacitance due to channel charge or different state of channel. This is the summary of overlap capacitance. Gate source overlap will be COX XDW. Gate drain overlap will be also equal. So, all the capacitances that are connected to the gate terminal with respect to source, drain, channel, and the body coming from different source, structural source, right? These are all due to structural properties of the MOSFET transistor. Now, let us look at the second source of the capacitance we mentioned. Diffusion capacitance. This is actually the third source. Diffusion capacitance or junction capacitance. Inside PN junction, inside MOSFET device, there are two PN junctions. A PN junction with N-type source with P-type body, N-type drain with P-type body. There is a depletion layer here, there is a depletion layer here, barrier, PN junction barrier. Across the PN junction barrier, there will be a capacitance formed that is famously known as diffusion capacitance or PN junction capacitance. This is a parasitic component. It will be present as long as a PN junction is formed. Now, you do not want this parasitic capacitance to be very large because then it will drain your battery charge. Instead of charging the output node drain, it will charge or discharge this parasitic capacitance. It will slow down the device and it will impose higher energy cost on the circuit operation. So we want to minimize these capacitances as much as possible. We cannot eliminate it completely because whenever there is a PN junction, there will be a finite amount of PN junction capacitance. But how you as the designer, you can control this capacitance. To be able to control that, you need to know what are the factors that will determine this capacitance. The factors are area and the perimeter of PN junction. If the total area and the perimeter of N-type source touching the P-type body is much larger and longer, you have larger p-n junction capacitance. If the depth of the diffusion, if the diffusion layer of the barrier is wider, capacitive plates are farther away from each other. Capacitance is epsilon A divided by D. If the diffusion layer is wider, D distance is larger, capacitance will be smaller. If the diffusion layer is very narrow, this P plate and N plate are closer, epsilon A over D. D is smaller, capacitance will be larger. If the area, overlap area, the bottom surface and the side wall of the source is much longer, there are more areas of the source will be touching the body area, so more p-n junction. Doping level. If the doping level of N-type and P-type region, by varying the doping level, you know that the barrier potential and the barrier is a function of the doping level. If the doping level is compared to N-type to P-type, on the P side, if the doping level is much lower, then depletion level will spread much further to cover more areas to get more holes neutralized. If the doping level on the both sides is much higher, the depletion layer will be formed at much faster rate because there will be a lot more electron and hole across the junction to cross over to come into an equilibrium, so depletion layer cannot spread. That is another reason why doping from the source side is kept at much higher compared to the body. For two reasons, because we want higher concentration of electrons to send through the channel for better conductivity. Other side, compared to body, I want to keep the doping density much higher from the source and drain, so the depletion layer on the body side spread much farther down, deeper into the body, so that effective p-n junction capacitance remains smaller, right? Because depletion layer spreading means the distance between N-type source and P-type body layer is increasing, so capacitance will increase. Terminal voltage also will be important, because if the terminal voltage, effective voltage between source and the body terminal remains zero, you have effective capacitance Q equal to C times V, 0, right? But if there is a finite amount of voltage difference appearing during the operation between source and the body for whatever reason, that p-n junction either will shrink if it is a forward bias, it will widen if it is a reverse bias. That will change the value of p-n junction. The polarity and the magnitude of the voltage effective at drain source and the body terminal will affect the magnitude of the p-n junction. So if you know this factor, then you can control the values to control the p-n junction capacitance. So now let us see how can we estimate the value of, yes.
So let's go back to the back of previous slide.
Okay.
If we're increasing the doping level, that will increase the depth of diffusion layer.
Decreasing the doping level on the P side will actually increase the spread of the depletion layer. Why? If you look at the fundamental properties of a p-n junction, so whenever a p-n junction is formed, this side becomes negative, this side becomes positive. After some electron crossing from this side to this side, from this side to this side, they come into equilibrium when equal number of electron crosses from this side to this side, making it negative, equal number of overcross from this side to this side, making it positive. With a much higher density, it will get, before it gets enough strength to repel further flow of hole to make it a strong positive, because this side has a lot more electron. So a much tiny narrower area of this side will be depleted because it has many electrons because of the higher doping density crossing over this. Each electron will neutralize a hole here. But because of the lower doping density, to find those that equivalent number of holes to neutralize, to create a negative layer here, it has to go further deep inside the p-value. So this side will spread further if the doping density here is much higher. So if those both sides has identical doping density, so spread of the depletion layer on N side and P side, you can consider, you can assume that they will be equal. But if the doping density is different, on the lower side, to cover equivalent number of carrier to combine source and the drain, so electron and the hole, it has to cover more areas because the density, doping density here is lower. So that is one way of controlling the width of the diffusion layer to control the p-n junction by playing with the relative doping density on the N side to P side. So that's all for today. Again, what I will do is next class we will be reaching the end of this lecture 2. But before moving to lecture 3, next Tuesday, I want each one of you to come prepared, read all the slides with lots of questions. I want to repeat from slide number 18 to 49 again, because you need to understand the operation and the properties of master very well. Yes. Okay. I will send email, maybe, but today this probe is behaving very weird. It is not changing. No, it's actually dependent. So, I use like 4 or 5 different texts as reference book. So it's just depending on which textbook I took the equation of field from. So I just took that. So that's why otherwise there is no difference. It's simply an oversight error. Yeah. Okay. Oh, yeah. I give me till Monday. I will ask because I will need some subscription to basically do the check. Turning is one option, but
I don't think so when you do it, show. Actually, it is not showing me.
Okay.
So that's why I'm more concerned that definitely it doesn't have a data. That's why it's showing this.
Okay. I want to see. Let's do that. Finish that, then we'll worry about the aging. Yes. Okay. So you will list the quiz? No, not next Tuesday there will be, because I have to finish lecture 2 first, and then the following week we will have a quiz. Okay, that's fine. This Tuesday we will not have a quiz because we haven't finished the lecture 2 yet.
I was sent an email about going out of town for
I know.
next week, so I just wanted to follow up on that.
That's fine. So yeah, so once you come back, let's meet and then go over the material. And if we arrange any quiz during your absence,